Hello everybody, welcome back to another episode of the problem solving series. In today's video we're going to be covering all things mechanical waves. So we've got traveling waves, characteristics of waves, standing waves, harmonics, wave speed. We've got a whole bunch of stuff going on, so let's just jump into it. So the previous video that I did was talking all about simple harmonic motion or periodic motion. There's actually a lot of characteristics of periodic motion that carry over into mechanical waves, so they're very closely related in a lot of the forms of the equation. So where we have this kind of wave-like pattern of how the mass on a spring moves, you know, for instance, either that or a pendulum, those are the two things that we talk about, that unfolds in a very late wave-like way in time. So a lot of those time characteristics we have are going to be the same for mechanical waves as they are for periodic motion. Namely, that's going to be our frequency, our period, the amplitude, and also the angular velocity. But for mechanical waves, we also have this wave-like motion dissipating out into space as well as in time. So we do have some new quantities and wave characteristics that we want to mention here. The first one that I'll mention that's arguably one of the most important is going to be the wave speed. So this is going to be so I guess I want to make a note here just because I think that it's important and maybe can get confusing. So the wave speed that we talk about here is not going to be the same as the speed of the system or the velocity of the system that we talked about in the previous video. So for simple harmonic motion, that v of t equals minus a omega sine omega t, that is describing the velocity of whatever object we have that's moving on our mass, on our spring, or on our pendulum at a period of time. But so the way that that connects to mechanical waves is that mechanical waves work as this kind of energetic disturbance is propagating through a medium, and the particles themselves, let's just say that we're thinking about like a sound wave traveling through the air, the particles in the air are going to move kind of back and forth in the same way that the simple harmonic motions move. It's almost like all the little air molecules are tiny little baby masses on springs moving back and forth, but the wave overall can travel through all of that. So the wave has its own speed separate from how those individual molecules might be moving. So just because we have so many V's at this point, so just try as much as you can to distinguish wave speed from velocity of individual particles or anything like that, because those two things, we don't have at this level equations that connect them, so we do want to separate that. So that'll be a constant. That's a characteristic of the wave. That's also going to be a characteristic of whatever medium you're in. So since these types of mechanical waves need a medium to move through to have those mini baby masses on springs, you can think of them as. This is also going to depend on the medium. So for this video, I'm really only going to talk about waves moving on a string as far as that's concerned. So for a wave moving on a string or a chord, we can also write the wave speed as the square root of the tension in that string divided by the mass per unit length, which we typically call mu. So another recycled variable, so this mu is not the coefficient of friction. This mu is going to be the mass per unit length. And just wait for everyone taking E&M, there's even more mu. So again, I'm just going to beat a dead horse. We want to be very, very careful with our bookkeeping, and that within the context of whatever problem we have, we know what our variables mean. The last wave characteristic that I need to mention is going to be the wavelength. So the same way that the period describes the length in time that it takes for one cycle to complete, the wavelength describes in space, the length in space that this wave cycle is. So the length of a wave cycle would be the wavelength, and that is going to be measured in meters. So this is going to bring us to what I like to call the bread and butter equation for all waves. So this video is just talking about mechanical waves. Later on in either sometimes they talk about it in the mechanics course, but more likely the E&M course, you talk about electromagnetic waves. No matter what kind of wave you have, transverse, longitudinal, any wave, this holds true. So this is why I call it the bread and butter equation. It's called the wave relation, and it's just that wave speed is equal to lambda times frequency. So love it. If you ever I don't know where to start, at least you know that you have that no matter what kind of wave that you have. I lied. So I am going to have another video on sound waves just because for the class that I am an instructor of, sound waves are their own chapter, so I don't want to make any of my videos too long. But since I did mention for waves traveling on a string, the equation that we have for the speed in terms of the quantities related to the medium, so the tension and the mass per unit length, I will also just mention that sound waves traveling in air have their own equation as well. That depends on the temperature of the air, so I will pop that up here, but it's just 331 plus 0.6 times the air temperature. That air temperature does have to be in Celsius, but otherwise you just plug in make sure that you're in a sound wave traveling in air first and foremost, then make sure your temperature is in Celsius, and then you can just plug in and get the wave speed if those are the types of givens that you have. Similarly to periodic motion, how I drew out all the three equations and also labeled kind of where the period, the amplitude, and all of those characteristics are and how they show up. I'm going to do the same thing for just for these mechanical waves. I'm just going to show it with the dimension on the x being the length, so that way I could draw the wavelength, because all the time domain stuff is going to be the same as for the simple harmonic motion. So we have the wavelength being this complete cycle. Now for waves, we can introduce some new vocabulary. So we have peaks, which is when we're at our positive maximum amplitude. Our troughs or valleys are where we're going to be reaching our maximum negative amplitude. And then when we're crossing the zero line, those are going to be called nodes. We can also call the peaks and troughs antinodes, since they're the opposite of nodes. They're at the absolute opposite of zero. They're at the maximum displacement from zero. Those will be more important when we're talking about standing waves, but I do just want to introduce it here so that when I use those terms, you know what I'm talking about. Another interesting thing that happens with waves is that if you confine types of waves to only move or kind of restrict their motion to be on a fixed length of whatever medium that they need to travel through, then we get what we call standing waves. So essentially the wave or the medium is, so it's a fixed length that the wave is stuck on, and the wave is going to just be moving so fast back and forth between that it starts to look like the string itself, or if you could see the air particles themselves are kind of suspended in this wave. The human eye, this is not actually what's happening. It's more so that the string is just moving back and forth between those states. So we're going to talk about our three configurations, but two main types. So we have waves on a string, and then we have waves through air. So to confine on a string, it would just have to be fixed at both ends. And for sound waves, this would be going through a pipe. The pipe has to be open on at least one end, so we call an open pipe when it's open on both ends, and a closed pipe when it's only open on one. And each of these configurations has their own rules for what constitutes a standing wave or an allowable standing wave. So the smallest frequency, largest wavelength that you can draw for any of these configurations is called the fundamental. So there are technically infinite numbers of waves that you can fit in any of these configurations. The lowest one is always called the fundamental. The fundamental wavelength and frequencies are indicated with a subscript of 1 for the general frequency or wavelength for any harmonic or wave mode. That's typically what we call when they're higher than the fundamental. They're indicated by a subscript little n. So now let's just talk about, I'm going to kind of keep those up there, that those are the general frequencies and wavelengths for these waves. So let's talk about the rules. So for waves on a string, it's going to be fixed at both ends. So the absolute biggest wave or lowest frequency wave that we can draw would be just one hump connecting those two waves. And I'll have diagrams up here that are much nicer than just my little bippity boppity boo finger demonstrations. So the lowest wave that we would have would be look like this. For any higher harmonic or wave mode after the fundamental, we would just be introducing more nodes and therefore more antinodes. So for the next one, we would have one more node that would go directly in the center of the two on either ends, and then we would have one wave connecting them like that, and so on and so forth. For open pipes, or for pipes in general, I guess I should say, at the openings is where we need to have our antinodes. So for an open pipe, the smallest wave that we can have fitting in there for our fundamental would be, like, say, a maximum at one end and a minimum at the other. This would give us a node in the middle, and that would be our smallest wave. And then for a closed pipe, we would have an antinode at one end where it's open, and then a node where it's closed, and that would be our fundamental for that. For all of these situations, for these three configurations, we can actually write the wavelength in terms of the length and that wave number n, where for strings and for open pipes, that n can be any integer. So starting with 1, that would be our fundamental, and then going up 2, 3, 4, 5 to infinity, essentially. But for the closed pipes, because of the geometry that restricts some of the allowed waves that you can have in there, so the ends can only be odd for the closed pipe. So I will also mention here that can get a little confusing sometimes, and that can be like kind of one of the tricky things that professors might do, because technically the second harmonic for a closed pipe is going to be n equals 3, and the third harmonic would be n equals 5. Since the allowable states are 1, 3, and 5, 3 is the second one that comes up, 5 is the third one that comes up, and so on and so forth. So just for closed pipes, just pay a little bit closer attention. But for all of them, for any harmonic of any kind, you can always write the harmonic frequency f sub n as the wave number n times the fundamental. So that won't change no matter what type of standing wave that you have, but the wavelength has a little bit more to it than that. So again, all of that I'll probably just cover myself, so you guys can screenshot that, and I'll leave that for you guys to do right now. And once you guys have that, let's go ahead and jump into our example problem and see how to work with some of these equations.
The fundamental frequency and wavelength for a wave are 200 Hz and 0.5 meters respectively. What is the wave speed? So since we have our frequency, I'm going to call this F1 since it's our fundamental frequency, 200 Hz. Our fundamental wavelength, lambda 1, is our 0.5 meters. We can just use the wave relation to get the speed of the wave. We'll have v equals lambda times f. In terms of harmonics, we could also write this as lambda n times fn, just to make sure that we're using the same harmonic frequency and wavelength. Both of these are going to be 1, so for us, I'll just do v equals lambda 1 times f1, and we'll put in that 0.5 and 200 to get 100 meters per second. if this wave is on a string with a linear mass density of 10 to the minus 4 kilograms per meter. So that's just mu. I don't have a mu key or way to write it nicely in this thing, but linear mass density is another term for mu. What is the tension in the string? So now we have the V from the previous part. We have mu is that 10 to the minus 4. And we want to know force tension. So we have an equation for the wave speed for waves on a string. That's V equals force tension divided by mu. Take the square root. So I'm just going to step through the math here first in variables before we plug in our numbers. So we're going to square both sides to get rid of the square root. We have V squared equals ft over mu, and then we'll multiply both sides by mu to get that out of the denominator. So we get a mu v squared is our force tension, and then we have a 10 to the minus 4 times 100 squared, and that is equal to 1 Newton. And then last, what would the next harmonic be if this wave is A on a string, B in an open pipe, or C in a closed pipe? So we have 3 different equations for these. So let's look at on a string. So we can say that lambda n is equal to 2L over n. Fn is equal to Fn is equal to n times F1. And for strings, we are allowed even and odd integers, so n can be all of those things. We're calculating n equals 2. I'm just going to circle that one. And, so we don't know the length. So this is something that I don't explicitly always write. But since lambda 1 is going to be 2L over 1, or 2L, we can also rewrite lambda n as lambda 1 over n. We just don't explicitly have the length for any of these, so that's also kind of a nice relationship to have. We're going to solve for lambda 2 equals lambda 1 over 2, where lambda 1 is 0.5. And F2 is 2 times F1, which is 2 times 200 is 400. So for string, lambda 2 is 0.25, F2 is 400 hertz. Strings and pipes, we'll see, actually have the same equation. So for pipes, well, the rules for where the nodes and antinodes, or the rules for how we draw them, are different since we're focusing on antinodes being at the openings versus nodes being at the ends. But it's basically just shifting the wave, but the amount of wave that fits in either is the same. So we'll actually get the same things for pipes as we do for open, as we do for a string. So I'm just going to go ahead and copy down these values, and then I'm going to erase this so I could do the pipes. I didn't leave myself quite enough room. And just in case anyone needs to screenshot. So for both of these, we had lambda n is 2L over n, which is lambda 1 over n. That Fn is n times F1, and that n can be even or odd. For C, our closed pipe, we have lambda n is 4L over n, but it would still be lambda 1 divided by n. Our frequency, the harmonic is the harmonic number times fundamental. But now for both of these, we have n can only be odd. So our second harmonic is actually going to be for n equals 3. So we are calculating lambda 3, which would be lambda 1 over 3, 0.5 over 3 would be 0.15. And I guess maybe the other way I'll show you, since we can also solve it this way, would be reusing the wave relation. So we have V equals lambda 3 times F3. So V over lambda 3 would be equal to F3. Our V is 100, and that would give us 667 hertz. Which actually, that's incorrect. That's not what point. So 0.5 divided by 3 is 1.67. So we're dividing by 1.67, and that gives us 600, which you would also get if you did it the other way. And those are our answers for that. So those are harmonics and traveling and standing waves.
All right, and that is all I have for mechanical waves for you guys today. Thank you so much for watching. I hope you found this video helpful. And until next time, happy physicsing!
Hey, Howitzer, you ready for your present from the Easter Bunny? He left you a pup cup. Oh, you dropped some.